Okay, so you have a couple of homework problems that need this technology. So let's look at how we could answer the question, what is the interest rate you need for your sinking fund to get to a certain amount in a certain amount of time? So it's impossible to solve this complicated equation for the interest rate and get I equals some complicated formula. It's not possible to do that. So there is a way to solve using technology. So if the thing you want to find out is the interest rate, let's call that x. So we put the interest rate x in this formula where I would be, well, the r, the interest rate r, and we graph y equals that formula in Desmos. And then we want to know, when is that equal to 100,000? So then we graph y equals 100,000 and look at where those two graphs intersect. So make sure you're seeing where all the parts of the formula come from. The $1,200 is the payment amount. Then here we have the 1 plus. Then this will be our interest rate R. It's quarterly payments, so we're dividing by 4. Quarterly payments times 15 years. So that's going to be 4 times 15 for how many times do you compound. Subtract off the 1 and then divide by that same interest rate. So I want to show you the graph. And here's the graph in Desmos. So this is a graph of if x is the interest rate, y is the accumulated amount at the end of the time period. So for instance, if I look at when x is 0.09, so when x is 0.09, follow this vertical red line up. Actually, let me make it a different color. Follow the vertical blue line up. That's x equals 0.09. Look at how the boxes are 0.01, 0.02, 0.03, and so on. So at x equals 0.09, it hits the graph, the purple line, at 149,340. So if your interest rate was 9%, so a decimal of 0.09, then your total accumulated amount would be 149,000. We want to know, when is the accumulated amount 100,000? So we're going to draw a horizontal line at 100,000 and say, what's the x value where this happens? In Desmos, you can either touch or click on the point of intersection, and it will tell you the coordinates. So if you want to end up with $100,000, your interest rate needs to be the decimal 0.0425, which is the percent 4.25%. So this is the only way to do these problems, and I'm pretty sure the two homework problems are 19 and 21, that this is the technology that you need for those. Know that this is a really small topic as far as the importance in this chapter, but I really like for you to see how technology can be employed to solve problems so that it will occur to you in your work life. Very likely you will need to use technology to solve problems. Okay, so one more topic in this section where we're looking at the future value of an annuity due. So let me flash back to the top. Well, not very flashy. My tablet does not want to scroll. If I talk nicely to it, maybe it will scroll. I'm having a technology challenging day. Okay, here is our formula. So this was the future value of an ordinary annuity, payments at the end of the period. So now let's go back down here to future value of an annuity due. So this language will show up again in the second of these two sections in 5.4, where the words annuity due go with making payments at the beginning of the period. So if we want to find the future value of an annuity due, we plug everything into this formula and we have payments of $750. And when you put the payments in at the beginning, it makes a difference. So let's look at a little bit of why it's different. Now you're putting the first payment in at the beginning of the period, and then at the beginning of year two, and the beginning of the last year. Now you're not putting any money in at the end of the last year. So the equation has to be adjusted for that. So you subtract off the one payment that you don't make at the end. The interest has to get compounded one extra time for this first payment that's getting made a year earlier than it was. So those are the adjustments in the formula. So it makes a difference whether the payment's at the beginning of the period or the end of the period. So your interest rate's 0.27, so that's going to be 0.0027 as a decimal. You're compounding semi-annually, so you're dividing that by 2. 15 years twice a year, that would be 30. So it's add 1 and it's an exponent of 31 minus 1 over your same interest rate, and then subtract off your payment because you're not making that last payment. Okay, and make sure that you can get on your calculator 22,977.02 is going to be your future value when you're putting the payments in at the beginning of the period. It comes out a little bit different. Okay, so that's knowing the payment, solve for the future value, and then just as we did previously with the payments at the end of the period and the ordinary annuity, you could also be given the payment and asked to find the future value. So in this example, we're being asked to find the payment. So we would divide both sides by the amount in the square brackets. So let's just write the equation out in the same way. We want a future value of 125,000. The thing we want to know is the payment amount. So we have 1 plus interest rate of 6%, so 0.06 as a decimal. Monthly payments, so divide by 12. The exponent is going to be 9 times 12, 9 years monthly payments, so that's 108, add 1, so an exponent of 109, minus 1 over always your same interest rate, and then subtract off payment again. Oh, and I need to make a little adjustment here. Inside the what you divide by, it's going to be square box minus 1, because see how we have a common factor of payment? So we're going to have 1 plus I to the n plus 1 minus 1 over I minus 1, because we factored out the entire term of payment. Okay, so we're going to have payment times, this is going to be giant, 1 plus 0.06 over 12 to the power of 109 minus 1 over 0.06 over 12. That has to have 1 subtracted from it. So I would figure out this big box of stuff and do 125,000 divided by answer. You're welcome to actually write out dividing both sides by that big block. It's kind of a lot of writing. So make sure you're doing the correct order of operations. and I'm getting $871.36. So that would be the payment amount you would need to put in at the beginning of each period to end up with $125,000. And that's the end of section 5.3.